So good Monday morning, everyone. Thanks for all coming so early. On a Monday morning, I'm obviously not Prashant Shenoy, as you might have figured out. My name is Mike Zing. Prashant asked me to give a guest lecture today because, from what I understand, he's traveling today. And so he asked me, to talk a little bit about multimedia streaming. That is also a very important topic in the area of distributed systems. One of you listening NPR this morning? National Public Radio here? They actually had a story about how Hulu and Netflix and all the others try to now get customers, regular TV viewers, hooked to their services to kind of have them subscribe and so on. So it's a topic that even makes the news, the regular news these days. So it's a very important topic, and I'll elaborate on this a little bit more. I'm actually a professor over in the ECE department. Before I took on the position there, I've actually been a research scientist and a research professor here in the computer science department. Some of you might know me. I know a bunch of the people working here, including Prashant, very well. So what I wanted to start with is give you an idea, actually, what are the constraints we're putting on systems when we talk about multimedia streaming. And the most challenging is really video in this case, right? So if you look at what I have on here, I hope you can read this all fine. One thing I wanted to mention, I forgot before. Please just interrupt me anytime if you have any questions. Right? I would like to keep this as interactive as possible. If something is not clear, if you want to elaborate on something, have more background, would like to have more background information, in addition to what I'm showing you on the slides or what I'm saying, just ask, please. We have the data demands and the data itself are much higher than what we are usually used with other applications. So if you look at the storage requirements, for example, for multimedia streams, if we look at 4,000 movies, just assume they're all kind of standard movie size lengths of an hour and a half. DVD size, 10 Mbps DVD size, we need a storage of something of the order of 27 terabytes. If we go to 50 Mbps, we have 40.5 terabytes of storage. 36 Mbps, Blu-ray standard these days, 97.2 terabytes, right? So it's quite, just from the storage side, it's a lot of storage we need just to store 4,000 movies, right? If looking at these libraries these days, there's a lot of movies that services like Hulu and Netflix offer, so they need quite these storage these days. If you look at 2,000 CDs, on the audio side, it's a little lower, it's a 1.4 terabyte in this case, right? So just alone from the storage side, there's quite a bit of a demand, and it puts a lot of load on the system. And then if you continue to look further, on the I/O side, if the service is very popular, you have many concurrent clients that are connecting to the service. They want most likely a variety of different streams from the system, right? So there's quite a bit of load on the I/O side of the server. As we know from streaming, it's very different to just FTP download, web page download. It's real time. Right? If we don't get information to the client at a certain point in time, it's useless. Right? We want to show a video with a certain frame rate. 30 frames per second is, for example, the standard. Right? If we don't get all the information for the next frame on time, we have large disruptions. We can deal with some tolerance, right? Loss tolerance, so we can use a certain fraction of data, and it still shows. You've probably seen that sometimes when you get this blockiness when you watch a movie that's, for example, encoded, right? So you can lose some of the information, but you cannot have it that all the information for a frame comes too late, because then it's worthless. Or you have to buffer, which we very often see these days by using these services, right? So we want continuous play out. So as you can see, we need very high data rates, right? If we want to continuously play out a DVD, say we don't apply any compression or whatever, we need data rates on the order of 10 megabits per second, right? Very different again from what we usually see. A Blu-ray is even higher. And then if you look at the capabilities, right? This is maybe not totally up to date, but very recent. We have mechanical disk, 400 megabits per second rate, and SSD RAM, SD-RAM hard solid state disk up to 1 gigabit per second of rate, right? And then network. Well, traditionally we have 1 to 10, we have even 40 to 100 gigabit interfaces these days, but the 100 ones are crazily expensive. They're usually used in the core backbone and not on servers, and absolutely not on clients, right? And then the buses, as you can see, we have 8 gigabits on PCI and up to 64 on the PCI Express. So that's kind of, you know, when you look at the stream of getting the data from a server out into the network, right? And there's a lot of constraints on the system itself. And then that doesn't include that you have any computing in real time, so that you don't have any other computation running. So everything else, like encryption, adaptation, transcoding, has to also happen in real time. So if you would do that, that would even increase it more. Encryption, sometimes, you know, you want to encrypt a video, so only a viewer with a key on the other side can actually watch that video, right? We don't want, you know, there's copyrights and all this. Adaptation, sometimes, you know, since bandwidth is not guaranteed at a certain level, you might want to change the quality layers. And then transcoding is another way of, you know, changing it from one format to another format, depending on what, you know, capabilities a viewer has with the client, if it's a mobile phone, for example, smartphone, or if it's a desktop, or if it's even an internet-connected TV with a much higher resolution. This all has to happen in real time, right? If this doesn't work in real time, we don't get the quality we expect. And so this is kind of a little bit of an uphill battle here, right? So it's a lot of, you know, challenges here on the system. Right? So what I want to talk to you about is give a short overview on multimedia servers. There's been a ton of work in this area in the recent history. But what I want to do is, after looking at the servers, I want to look a little bit more and take a look at the system, right? And tell you what we did over the past years to analyze, you know, traffic and demands for these systems and what we can learn from that to improve the systems, right? With different technologies, by using caching, prefetching, and then even look at the recommendation systems. How can we use the information that we get? You know, all these online services have recommendation systems. They tell you what you might want to watch, right? They have lists where you show this might be of interest for you, how you can use that to improve the system's performance. Since these systems are very, very popular, we really use, or what's used for these services is really distributed architecture, right? Shouldn't be anything new to you. I'm pretty sure you have heard about this, what you call, you know, it's kind of several tiers, where you have the top tier, which are the master servers or the origin servers, and then you have a distribution architecture with regional servers. Sometimes they're also called maybe top tier caches and lower tier caches, right? So they're having cache functionality, and then you have local servers, and then we have the end systems on the bottom of the chain. So it's a distribution system, which we often see for all kinds of you know, applications in the internet to make it scalable. We see this for you know, regular web traffic, regular web data, web applications, and we have seen that companies like Akamai actually made it their core business to offer this distributing system. They sit between the origin servers or the master servers and the viewers, and provide this kind of you know, distribution here with the intermediary servers in between. So we have the origin servers, we have the proxy servers, and then the viewers down below. And there's a lot of dynamics happening here, right? Because what we originally want to do is we want to place a piece of content as close to the viewer as possible. Any idea why?
Latency issues.
Latency issues. Other ideas?
Cost to transmit?
Cost to transmit, right? Bandwidth consumption, right? If someone like Comcast can keep the data in their residential network, right? They don't have to pay for the bandwidth usage up here, or don't have to get a bigger pipe into the core internet, right? So if you can keep it as low as possible, that's kind of preferable. So if you know, if you could take your hourglass and could predict into the future what these users here are going to watch, right? Then you can actually do a very good job. Unfortunately, that's not really 100% possible, right? So you know, there's this focus on like how popular is our data, and then you know, also sometimes this is a high-level view of this hierarchy. There's different variations of this hierarchy, all the way down to being able to use peer-to-peer services as a distribution mechanism, right? We have seen that for some of the live streaming services, some other services where this is used. So when we look at, you know, the servers, the hierarchy, let's take a quick look at the single server, and that's something that's, can I shut the lights on front a little bit up? I hope it's a little bit easier for you guys to see. Is that better?
Yeah.
Does that work with the camera?
Yeah, no problem.
So you know, you guys, I think I'm sure you know all about operating systems. When we look at the path for retrieving data, right, we go from the file system to the application to the communication system, and often we have to go from kernel space into user space and back into kernel space to get a video out onto the network, assuming we have a canned video that's stored on the disk, right? And now let's see this. Now think of this as happening 100 times, 10,000 times, you know, because we have a lot of load on a lot of viewers wanting to watch this video. So you can see that this puts a lot of stress on the system, so on the server, so to speak, and you can optimize a lot of these things depending on the you know, on the application here. This has gone all the way down to people looking at file systems. Right? There's a lot of research, for example, on multimedia file systems. Actually, Prashant has done some work a few years back in this area. Right? So how can you optimize file systems based on multimedia? That's one thing. How do you do searches? How do you, you know, collect the data from the disk is one of the things. Another one is actually memory, right? Because you put some of that into your memory before you put it out in the communication system. Right? Not in your memory, in the computer's memory, obviously. And so that are important things to think about, and they are always under the constraint of having to do this in real time, right? Even the slightest delay can have some impacts on the quality the user experiences when he or she watches the video, right? And what we're not showing is actually what's happening all the way down here on the network, right? We're not even focusing on that. So the server internal challenges are actually the data retrieval from the disk, right? And then there's the important resources here are the memory, the buses, the CPU, the storage system, and the communication system. Right? So these are all the systems that you that have to be looked at when you look at multimedia streaming servers. And if you're interested, there's a lot of work out there. I don't want to go in all this detail. So one example that people have been looking at is, for example, to maybe not having to go into the application and not changing over into the user space, right? So there's work on, can you actually go by packaging, you know, your data into whatever protocol format you're sending out here in the kernel, right? Because then you save that context switch, right? Doing certain things of, you know, we will talk about caches in a distributed way, but even what kind of information do you cache in your memory locally on your server? If you know again about, you know, certain request patterns of the viewers, you can keep certain information in your memory, right? Why flush your memory if it's needed again in 10 seconds or so, right? So these are the things researchers focus on in the terms of multimedia servers, the servers alone. So a lot can be done by optimizing the resource utilization. And so if you look at this, when we look at the timeliness, right? So what I want to show you here is actually we see time on the x-axis, and then we see the data offset for just one video, right? So depending on what you have, what kind of format you have, when you start at T1, this is when you want to watch your video, right? So you start the play button. You have a play out, right? So sometimes you have a variable bit rate. Some videos have a variable bit rate, so your play out rate varies over time, right? It depends on the encoding format. Other times you have a constant bit rate, right? Let's just go with the constant bit rate in this example because it's a little bit more straightforward. So you have a constant bit rate. This is how you ideally want to play out the video. This is on the client side. This is on your computer, on your TV, on your smartphone, right? And so if you look at this data offset, now you can go backwards, right? You can say, if you want to do this, you must start retrieving the data a bit earlier, right? If you now start retrieving the data, you will have a delay. Right? So you know, if you look at the network part, right? Oops, I'm going too fast. if you look at the network part, it might be that your data is actually coming through the pipe in such a fashion. Right? So what you need is actually, you have to start doing this, start the streaming at the server side a little bit earlier, right? And then buffer on the client side to smooth out some of these effects. Right? And then what comes in addition is actually the sending, right? So you know, here's this assumption. Let me just finish that because then we have everything on there, right? So here the assumption is, well, you know, there's some changes through the network, but it's very similar. But it could be, these two lines could be quite significantly different, right? Based on what's happening in the routers and the links in between. And then you have your send function and your read function. And again, between the read function and the send function, it's not constant, right? Depending on how much load is on the server, that might change over time. So kind of, you can work backwards from that, right? Based on some information you have. If you want to play out video T1, you can actually see when you would have to start reading that information, right? So since we cannot actually foresee that, we always see that there's a little bit delay by all the services we're using today, right? We always get a little clock or a little buffer or something like this until things start, right? This is because it takes some time to get things off the server. You have to buffer a little bit to smooth out some of the networking effects, right? So that's what's happening, right? So kind of, you know, when you would design such a system, one second, you have to look into this kind of effects. Yes, please.
Okay, so considering this slide in the previous one, it seems that the time between reading from the file system and sending is just a fraction of the entire delay you put to start playing.
Yeah.
So it seems that even if you were able to directly send from the file system to the network card, if you can bypass this part of going to the user mode, you're actually just gaining like little latency in terms of one particular video. But perhaps the real advantage of doing that is that you're able to deal with more extremes at the same time, rather than one.
So well, just to illustrate this, I always take one example, but you now have to think of the server handling hundreds or thousands of requests, right? Absolutely right. And that's where you have to. For one video, the improvement looks small, almost negligible. But if you take the bigger sum, then you get the really big improvement, right? So that's also like when we look at distribution architectures, right? We wouldn't need a distribution architecture if we had 10 users, so we could easily serve that from one server. But now we have millions of users. We really need that distributed architecture with the caches and the other servers in between and the different hierarchies. Okay, very good question. Any other questions on that side? So now I want to mention a couple more things. Number one is this is becoming more and more important, not only on the video streaming side, but this is also important as games. Even more because games are interactive, right? So you have delay both ways because the clients are, you know, if you have like a first-person shooter game or something, it's playing against each other. So information has to go to the server and come back to the clients again, right? So this is one part where this is also becoming important. So when I talk about multimedia, I always take video as an example, or as the example, but there's a bunch of other multimedia applications where this is equivalently important. Another thing is actually, this now gets together with what's happening in cloud computing. You guys know OnLive? Have you heard of OnLive as a service? It's actually a game. They do games. One of the more interesting examples I found recently is actually they now what they do is they run a Microsoft desktop for you in the cloud, and you can use that on your iPad. Well, my iPad's OS X, right? So how's this working? What they do is they run the whole Microsoft OS and like Word and PowerPoint and all these applications on a VM in the cloud. And the only thing they do is they stream the video frames of that image of that screen output to the client. So I don't do any calculations. I just get new frames, and you know the mouse commands and all the stuff gets sent back. Imagine again, latency and so on are really, really critical here because it makes your experience very, very different. So streaming also becomes important now, where cloud applications are used for thin clients, right? Where you don't really have any high computational capability on the end user side. And the last application, I think that's going to take off quite a bit pretty soon, since we're seeing 3D TVs, 3D movies coming out, is really the 3D streaming. And depending on how the 3D streaming is realized, you see that the bandwidth even goes more, right? Goes up more because you have more data. Sometimes you have 3D approaches where you have different viewing angles, more streams that have to be transported, right? So this is a topic that will probably be of high interest for a long, long time, because there's more applications, there's more challenges through new formats going on. So with that, I want to stop here and see if you guys have any questions before I go on to the next topic. Okay, so I want to give you a little bit of an example on the challenges and in the system design when you look at multimedia streaming systems, by presenting you some of the work we did in the past years. And so what we are looking at is actually YouTube, right? And why I want to talk about YouTube is actually because it's a little bit of a different animal, right? There's a new challenge. Why is YouTube a different animal than the other services? Any idea? Who makes the content that's on YouTube? Users, right? It's not Lucasfilms and Disney and the big producer. Not always, right? There's some special needs there, but it's basically you and I, right? And what is different with that when it comes to scheduling? No one actually knows when new content is made public, right? So it's really, really hard to predict what's going to be popular in the next hour. With a service like Netflix or Hulu, it's a different story, because Netflix and Hulu, determine what's been available over their streaming services. So they know in advance when they put a new movie out, right? So I could imagine if Netflix, for example, puts one of the movies out that won an Oscar, they know this is going to be probably pretty popular. There's actually now, there's a site, I think it's called Hacking Netflix, that actually gives you for each week the new movies Netflix is going to be put on streaming, right? So people know that. And so Netflix know that this will be most likely very popular. So they can pre-distribute these videos in their hierarchy. With YouTube, that's pretty much not possible, right? Because I can put, Sean could go and put this online with what you guys are just recording here right now. In an hour, I would say, right? It's probably not going to be that popular, I'm pretty sure. but who knows what's going to be popular, right? So there's a pretty big challenge in it. So our distributing systems, as the ones I showed you before with the different hierarchies and the caches in between, actually of any help, right? So what we wanted to do is actually we wanted to actually see what's happening today, when we did this measurement with YouTube, and observe, and then see if we can, based on the observations we have, if we can make any improvements. So just a quick overview here. I'll give you a quick motivation on that, and then tell you about the measurements we performed, and then how we use these measurements to look at certain distribution infrastructures, and what we can take away from that, right? So it's probably, this is a little bit of an older number, but you guys know it by yourselves. This is a very popular service, right? I think now it's like, I don't know how many videos I've watched. I have it somewhere, the exact numbers, but there's this incredible high number of videos being watched on YouTube every day. There's even a very surprising high number of new videos put online every day by the users, right? So this is a very, very popular service which puts a lot of load onto the system. As I mentioned before, it's very different from traditional video on demand because it's user generated, right? So it's hard to predict. What we were looking into is actually how's actually the access from a campus network, right? Well, there's two reasons for that. Why we wanted to do that. Number one is we had a means of monitoring the traffic going in and out from this campus here, and the second one is actually we wanted to get a local idea. Why did we want to get a local idea? Well, globally you can get at least some idea about the YouTube popularity. How can you get it globally?
You can go to the press page.
Right? You can go to and use the API and look at the views, right? So theoretically, you could even like go through all of the videos that are available, right, and look at the popularity of the views and kind of have a popularity ranking. A bit tedious because you have to crawl millions of videos these days, but it's possible. And actually, some researchers from Korea and Telefonica in Spain had actually done that before. So there was some global idea. But as I showed you before on that picture, right, we are kind of interested in getting the content as close to the user as possible. So maybe the global information is not necessarily what you want. You want to have some information about what's happening on the local link, so to speak, right? Because that's where you have the most impact, right? And so what we also wanted to do is we wanted to compare that then to our data with the global popularity that has been already reported by others. So methodologies: monitor YouTube traffic at the campus gateway, obtain the global popularity, look at the video clip traffic that's actually generated. So we did a little bit of statistical analysis on that. And then do trace-driven simulations for various content distribution approaches. What are trace-driven simulations? You, instead of, for many simulations, you use stochastic approaches to generate your data. You assume like, Poisson arrival rate or something else. What we did here is actually we used the information we had from our measurement data to use that as input for our simulations. And I'll give you a couple of details on that later. So what we did is here, first of all, we had to re-engineer YouTube a little bit. We had to figure out how does it really work to make sense out of the measurement information here. So what's happening is, a client goes to the YouTube page, does a get message. What you get back is actually, when it comes to the streaming, you get a redirect message from the web server to a content server, right? With that redirect message, you then actually get the actual video stream, right? So what we were interested in is this kind of, information flow at these messages, because with that, we could see what client is requesting what video at what time, right? That was the important part. And we have so it's just an example of the message. I think this is not too important. But what we had for the longest time is actually a monitoring box on one of the gateways between this campus and the internet. Right? So we could see all the traffic that's going in and out. I always say that, no worries. We have an agreement, or we have, OIT makes us anonymizing that information. So we know all these IP addresses are anonymized, and so we just can make conclusions on the average size, but we have no individual information. Okay? So this is kind of the process we set up here. And so we started monitoring this traffic. And when we get this, this get and the redirect information, we use that and analyze the information. And so what we looked at is the duration of the streaming session, the average data rate, and the amount of transfer payloads, in addition to the requests and what content has been requested. So what you see here, we took the 3 different traces. You see this is a couple of years back. Oops, I'm looking forward in the year 22. No, something's wrong with the forward year. So this was all 2008, 2009, right? What you can see here, we took different length traces just to see, how things change if we look at longer or shorter time periods. And you see here the different unique clients we could identify in our traces. We could see the amount of different videos that were requested. Videos that were only requested only once during that time, and then videos that were requested multiple times. Right? So if you have video A and it was only requested once during this 12-hour period, it goes in here. If you have video B and it was requested, for example, 2 or 3 times, it goes into that category. Right? And so here's the first interesting result we see. Look at this ratio here, right? So no matter what the lengths of our traces, right? But there's a couple dots behind it. I'm sure that it's pretty much similar, right? So that's one interesting observation we made. Number 2 is there's only so much you can actually do with caching, right? Why?
Because it's only worth caching.
Yeah. Right. So this is one of the big problems for YouTube. Right? There's only a little bit. There's a lot of clips that are requested once. Right? So then, you know, this is on a high level. We also looked a little bit closer into these 3 streams. So what you see here is actually the number of requests over the cumulative CDF here, and you can see here there's a lot of requested a lot of the requested only requested once, and then you see that there's like one here that has maybe 80. What's this? It's just 10, 20, 30. No, only 40, right? So there's a couple of videos that have like in the 10th, or I think we got some here in the later cases we had some that were, there's one that got almost 100 requests during at the same video, right? So here you see the distribution for the different videos. So you can see there's a high portion for videos that are requested only once, and then there's another section of videos that are requested multiple times. And you clearly see along, you know, if you turn it around, you'd see that if you did a regular CDF, you'd see quite a long tail distribution. Actually, I think I have another graph where you see it here a little bit better. Well, still not turn around, but what you see here is actually the number of requests, and then we have the requests per video over the requests per video over all requests, right? And again, you see here that there's the single requests is very high, and then you see how there's multiple requests here, but really requests in the high numbers, you have only very small portions here, right? And then you see here the outlier, where we had somehow this video was watched 140 times on campus in this period. Go ahead.
With the previous statistic 2 slides ago, was that over all requests or over all videos? Over here. Okay, that's per video stats.
Yeah.
Okay, so
it's not over all videos.
So what proportion of all requests are repeat requests?
It's a good question. I don't have.
That would give us a better idea of how much caching helps.
Yeah, I don't. I have it in the paper. I would have to look it up, to be honest. I know I have it. I don't know why we didn't put it on here. It's not on the slides here, but it's in the paper. We'd have to look that up. I don't have that in my hand. So. But it would be a little bit higher, obviously. So then we had our local results, and we made some observations. So what we did is we went and looked at how what's the popularity of these videos we saw in these traces, right? So the nice thing is when you get a video, when you monitor a video request to YouTube, you always see this identical hash they use for that video, right? So you can actually use that hash. If you copy that hash and put it into YouTube, it actually shows you it finds the actual video. So with that, we could actually also look at the API and find the global popularity. And then we ranked the video not amongst all the videos, but with all the set of videos that had requested from our network, and ranked them. And globally, ranked them on the global data and then on our local data, and compared the correlation, and we couldn't find any correlation between them. So that was an interesting result for us, because if you want to do a good job on caching, the global popularity is not necessarily very helpful, because there's no correlation. So you couldn't go and say, so someone requests a video, right? Your cache is already full, and now what you could initially think of is, well, let me look up what the global popularity of this video is based on the information YouTube provides me, to see if I should cache that video or not. Right? If the global popularity is high and we had a strong correlation, then it would most likely make sense to cache it and replace an older video with that new video. But since there's no correlation, it's not really okay. Right? As I mentioned, either the length of the measurement or number of clients seem to have an effect on the local popularity. And then we found a couple of videos, like if you go to this link, this shows something happening at UMass, on the UMass campus. For sure, it's probably not a total surprise that videos with local relation had a higher popularity, for sure. And probably, if we would now look at the you know, the university starts making these little video clips to promote the university, stuff like that might have a higher popularity, which is absolutely makes absolute sense, but it again is not reflected in global popularity because our campus population is a lot smaller than, you know, the whole population of YouTube watchers. So we did a couple more things, and so what we looked here is actually where the request per client, right? So here's some of the information you were looking for, not directly. So this is the videos we had with multiple requests from the same client. Right? We were also interested in who gets multiple requests from the same client, and here's are the total number of requests. And so we looked at, you know, how many requests, what's the maximum number of requests from the same client. And so here you can actually see the distribution, and you see again a couple. There's one client that was very active, and then you see a lot of clients that just watch one. Right? And so you see this for all the three cases. That's not very different, right? So we had all this information, and now we thought we looked at. So how can we actually? What would caching actually improve, right? How can we use something that would really cache this information? And we looked at two approaches. Peer-to-peer and proxy caching. So we took the information from the traces and then created our own simulator and ran simulations on it and see how this would, you know, how caching would behave if we use that. So before we could do that, what we also wanted to do is we wanted to use the stream flow analysis to make our simulation as realistic as possible, by getting some information about the duration of the videos that were requested, the number of packets, the payload size, and the rate the users were streaming to video, right? So now we know how long a video is watched, right? Look, it kind of makes sense, right? So the average length is like 1.5 minutes, something like this, right? Because they're very short clips. There's actually some very long ones, and some, you know, some are just still images. Some very short ones. Here's the number of packets. Here's the payload size, right? So you have an idea. This is very important because if you want to simulate caches, then you know how much storage you need, or how much space you have available or not available, or when you have to replace information on the cache because there's not enough space anymore. And then there's the rate, which is interesting how the users will get this stuff. So the first approach we looked at is actually peer-to-peer approach, right? So no cache. Go ahead.
Could you go back one slide?
Yeah, sure.
So is this table just to illustrate what the data looks like, or do you really use the requests in the trace?
We use the requests in the trace.
Okay.
But we use the requests in the trace most with basically this information, right? So when I request a video and I simulate caching, right? I know the time when it has been requested, when the initial request has made. Imagine now my cache is empty. I say, okay, this video is go through the cache to the user, so it's cached. So I need, you know, at least this average amount of storage. Or if we have the individual information, we can say we need that amount of storage on the cache. Right? So that's what we track in our simulation. Now the cache fills up, and now I have to replace things. Right? So if I take one video off, I get so much free space. Can I store the new video on there? Right? So that's how we. So that's your question.
I'm afraid I didn't understand. Why do you need the average? Why don't you just use the payload size of the particular video that was requested instead of the average?
Oh, this is just for statistical. We just did the average for.
To illustrate the.
Yeah.
Okay.
For, you know, just to get an idea what the average is of the
Mm-hmm.
right? I think we used the individual payload size in the simulation.
Right.
Okay. So the first one we looked at what happens if we don't have any infrastructure, if we don't use a cache. The only thing we do is actually we assume that a client watches a video, right? Oops. And then would store that video, right? Let's say video A, for example. And then client B at time t plus x, but then if he or she were interested in the same video, could get it from that client, right? So what we did is actually, since we knew when the client A requested that video, we had this time information from our trace, right? We did simulation where we said, okay, let's just assume that this client has a 30-minute window where it's active, right, where it's up. Because what we don't know in peer-to-peer systems is actually how long is this client going to be on, right? And so based on that, we did a simulation. Again, we wrote our own simulator. And as you can see, based on these different traces, when we look at, what we show on the x-axis here is how much of data, of caching space we make available at each client. You can actually see how the hit rate improves, right? Hit rate is actually how many of the videos that are requested multiple times after the initial time can be served from one of the clients in the local network in this case, right? So you don't have any traffic going outside your net, outside your local network. And so you can see actually that you have a little bit of improvement. For sure, you cannot go above the theoretical maximum of the 23% we had shown in the original analysis, but you can see how that actually can improve your hit rate, and so reduce the traffic coming from the outside, and hopefully also improving this viewer's performance, because it's less delay, it's less prone to loss and all this stuff, because it's not going across the backbone. Okay, so that's what we see here, and as you can see, so this is actually, from a gigabyte of space on it, kind of all these the graphs level out, right? The different slopes level out. So if every user would donate a gigabyte of space, the system would get the highest hit rate. Now, there's already quite a bit of controversy if users would really do that. So we said, well, why don't we look at the next scenario where we really had a proxy cache on the gateway, so everyone from the network could be served from that cache. Here we just did a real simple FIFO replacement, so when the cache was full, whatever came in first goes out first to make space for new requests that should be cached. And so here you see these different traces, and so here we could go up, you can see that how you can improve the hit rate, and what you see is actually we need a much bigger cache size, but this is a gigabyte, right? This is a terabyte. So if you have, is that correct? Yep, right? So even with a terabyte, you could go over 20% hit rate, so to speak, right? So a terabyte is not really something very expensive these days, right? So you can, if you put a cache into your local network, you can get. Oh no, this is megabytes. Sorry, I was wrong, right? This is 100 megabytes. This is a gigabyte.
10 and 100.
What?
That's 10 and 100 gigabytes.
No, I confused myself. This is 100 meg. This is a gig. This is 10 gig.
Yes.
And this. So sorry, I was totally off. So 100 gig is actually what you need, right? So this is not much, right? This would be a very simple piece, a very cheap piece of equipment. You would install that to get this effects with caching. Now, since then, we didn't know that in 2009, but if you check now, there's a Google cache on our campus, right? So Google is actually doing this by now. They're putting, actually, Google owns YouTube, right? They're actually putting caches in different locations to improve their streaming service. I think they use it also for searches and mails and maybe other stuff. Right? So, but we didn't see that behavior actually in 2009. So how did we come across that? When we did recent measurements with local clients, all of a sudden we got a campus IP where the videos are served from. Right? And so that made us realize there's something in between now that is doing that. Okay? So that are the results we got for this case. There was actually work in this area had been before, so I told you about the guys who did the global measurement. That was presented at IMC 2007, and then at IMC 2007 there was also some people out of Simon Fraser, I guess, that did some work, but they could only monitor a predefined set of YouTube servers. we could really do a measurement all across the board. And the measurement was a little bit limited, and then none of them had done. We showed that video clips of local interests have a high popularity, and we looked at the different distribution infrastructures and how they could improve this service. Right? And again, as I mentioned, later on, Google is actually doing this service. They're using a caching infrastructure these days. Let me stop here to see if you guys have any questions. Go ahead.
So I guess those caches that you talked about, they use just regular policy, at least recently used or something.
I was just, for the simulation, we just did 5.4. We did we did some experiments we released recently used, but it wasn't a dramatic improvement. But because of that, you know, it's not, the popularity is so different from all these other servers where LIU really works fine, works well, right? So there's this unpredictability in here that is, you know, hard to manage. So there was no significant improvement when we used it.
Right. I guess it was not the focus of the work, but perhaps there must be something smarter they can do in terms of checking whether similar users, whether users are similar, and if one watches a video, then you can cache that video because the other one is going to watch it again.
But actually, there's something smarter.
Oh, okay, thanks.
Very good question. So I don't know if this is the smart thing you can do, but what we figured out, what we then thought afterwards is, you know, so first of all, prefetching, right? If you get information already into the cache before the user even starts watching the video, that's again, you know, it reduces your delay and so on, and probably leads to higher quality and better experience. But the question is what to prefetch, right? What do we want to get into? So, you know, I think I talked about this already in some detail. But our initial motivation was, you know, this is often what you get when you watch YouTube videos, right? It's a little wheel turning, but that's not really what we want to watch, right? And actually, I think even today, right, at noon, Ramesh is going to give a talk in the systems lunch about the work they had at IMC last year, where they looked at video streams and showed that 2 seconds of delay even, or 2 seconds of buffering already turns users off. They go away and try to do something. It's just, people cannot wait anymore that long. So if you have a chance, and with some free lunch at noon, you should probably go over there. I think, am I correct? This is happening today? Did anyone see an email? Right, noon today. Okay, so that was our initial idea. So we want to, you know, well, that's our idea, but we want to make sure that's actually the case. So what we did is we instrumented clients, or no, we actually asked users to watch YouTube videos, which they're always happy to do, and have Wireshark running so we could get traces, right? So we asked our friends because this was totally not anonymized, so we actually saw what they were watching, right? And at different locations. So actually, this was me going to a conference, right? So I did this from a hotel, also, right? Coffee shop, university, different dorms, and so on. And what we did is actually we analyzed, you know, how many times. So we asked them to watch, I don't know, forgot 10 videos, yeah. And so how many times did the video player actually work fine, and how many times was it disruptive with buffering or not pausing the video? And you see my hotel, they had really terrible internet connection. So that ruined the whole statistics a little bit. But so we actually found that 41 out of 117 playbacks contain pauses, right? That's a pretty bad number. And we actually continued that a little bit by changing this a little bit. So we had a system. We created something that automatically would retrieve YouTube data, and we did a Planet Lab study. So we all ran this automatically on nodes all over the world actually, and it doesn't change actually. The numbers are relatively similar. And we automated that complete and had that happening on locations all over the world. And so this is something which is not great. And so what we also saw is that when we analyzed that 22% contained more than 10 pauses, right? So you watch a video and it interrupts 10 times. This is totally annoying, especially if you think of YouTube videos being relatively short. Right? So why is this happening? Well, something is happening on the backbone, right? This network is not good enough. Maybe servers overloaded, cache is overloaded. It's not in the cache, right? So, you know, we sat down and said, yeah, how can we improve the user experience? Well, do you have a question? Okay, sorry. So, well, there's one thing, is actually this prefetching, right? If we somehow know what the client wants to watch in the next hour, so we could get this information already to the cache, or to the closest by cache, or locally into his kind of, you know, local cache, so to speak, and use that information. But how do we know that, right? So the idea is that you have like a kind of a prefetching agent that selects this from an architecture, from an architecture point of view, the idea is you have a prefetching agent that selects what videos should be prefetched, and you either select them to your proxy or select them locally onto your machine, right? And so we call these two schemes as the PF client, which does it directly on the client, and then the PF proxy, the prefetching proxy, which is does it to the proxy that serves a wider range of clients. So these are the two schemes, and these are the naming schemes we approach, and these are the two naming schemes we used here. And then, you know, the PA determines the videos to be fetched from incoming requests. And what we did is we simply said, let's make use of the recommendation system, right? So when you watch a YouTube video, you always get a list of the referred video list. That's called the referred video list, right? So you have actually 20 videos on that side. And so we said, now what if someone watches a video and we just start prefetching what's on that list, right? Does that actually improve something? So, and we actually looked at two ways. One is actually when someone did a search, right? You can do the same because you get a list of searches. And then you prefetch a certain number of videos shown on the list, or you can do this for the related videos. And then we did this for up to n videos, and we showed the different ends here. So the advantage of that is, it's simple. We don't require any additional data, right? There's no huge collecting of whatever kind of information, global information, APIs, and so on. But how effective is that? Is that really effective? Right? You're shaking your head?
Yeah, because if you prefetch 20 videos, user might watch only one of them. So you wasted lots of bandwidth in prefetching.
Let's see. It's a good guess. So again, we took the traces we had. We actually got some new traces. They're a little bit more recent, right? They're from 2009 and 2010. You see here the number of requests. This is a very high request. I always explain people here, you know, when you do measurements, you got to really look close in your data. So when we took this measurement, this number of requests really low, right? January 8th, when you're on a US campus, what's usually happening at this time? Everyone's at home, right? That's usually the undergrads, at least, are not on campus, right? So that was not a good time to make this measurement, we realized afterwards. But you know, now you got to think of all this stuff, right? So when you do measurements, you can really think these things through, right? There's a lot of things you can do wrong, I can tell you. What we did is also we retrieved the search result list and the related video lists via the YouTube Data API, right? So we knew actually for each of the videos that were requested here, how the list for search looks and what you get on the related list, right? And so based on that, we used that data for information. Now, to come back to your question first, we wanted to see how often the user uses actually the related videos and the search result, right? And so what you see here is actually the two of the traces we analyzed. We couldn't use the first trace because the header wasn't long enough, so we didn't get some information. Great. Okay, so we can only use trace 2 and 3. And so here's the distribution, right? So if you look at the trace 2, for over 30%, users use the related video list. For a little bit less than 30%, they use the search list. Then they use YouTube pages and then external links, right? How do we know that? When you get the play URL, there's actually an ampersand and it says search, related list, or whatever. So it identifies it. I think they use it so YouTube can actually use it. They do this for their own creation of statistics, right? So we see that. So these are quite often used, right? And so that what made us kind of more confident that we can do something with that, right? And especially since the related list and the search results have the highest portion here. So the evaluation methodology here in this case is, again, we do trace-based simulation. So we look and we issue these the request based on actual user requests. We know videos requested. We know if it has been requested from the related list or from a search. Based on that, we know through the API what would show up on the search or on the related list, and we simulate a prefetch of this. Right? And so again, evaluation metric is how many can we serve from the cache based on that approach, right? And we determine the hit rate. And so this is the results we got from the simulation. What you see here is actually, we looked at how many of these videos we prefetch on this list. So capital N says, you know, if you see a total of 25, right, we prefetch only 1, we prefetch 5, 10, and so on. Right? This is the simulations we run. And here's the hit ratio. And now all of a sudden you see, wow, look at the, where's my legend? This is related videos and over N, and we did this with the proxy approach, right? That goes up to a hit rate of almost 80%, right? So there is some benefit from that. And I'll actually show you later that if we get to it, that Professor Gao over in ECE and our students have analyzed, and we have actually looked at this, that people watch multiple videos. So there's a high percentage of people, I think we have analyzed the traces, something between 40 and 50% where they watch 2 or more videos in sequence, right? And that's where this is beneficial. Yes, please go ahead.
So if you're doing prefetching at the client, and can't it hurt the performance of the download, the video he's currently watching?
Yeah. Yes. But you don't have to necessarily do it exactly at the rate as you would play it out. Right? You could actually do this a little slower. Right? I have a slide on that in the end when we work this out. You see how the different schemes perform? This is the 0.4 is, I think, the regular line where you just would use standard caching in this case. Right? So you can see that the prefetching really. Now there's another. Oh, wait, it comes later. Sorry, give me 1 second. So if you combine caching and prefetching, then you get even a little bit higher improvement in this case. Right? So if you cache the videos that are requested anyway, and then prefetch what you see in the search and related list, right? You get a slight improvement. It's not too much, but a slight. So now, what we figured out is what surprised us is actually, we got this very high hit rate, right? But we have only roughly half of the requests are coming actually from the related list in these traces we have, right? But we have an 80% hit rate all the way at the end. And so, what we did is actually, we analyzed also where are our requests coming from, right? So, when we have this 80% hit rate, right, you have, when you go all the way to the last column for the n equals 25, you see that the related list is this blue column, and then the yellow dotted column is actually a search result list. So there must be some synergy, right? So that, you know, some videos that show up on the search list must also be showing up on the related list, right? And that's why you get this high hit rate, just when you use the related list. Right? So for prefetching. So that's just, you know, the conjecture we draw from that. We don't have a real proof of that, but since we know when we get the hits, where this request originated from, we see that the related video list doesn't make up all this. Right? So there's just some luck, so to speak, right? Because there's some overlap. And so that helped us. And we think also that the recommendation system is a good indicator of the topic of interest. Right? So we can use the recommendation system. And it's just, you know, just so to speak, at our fingertips. The information is just there. It comes down with every web page. So when it goes through a proxy, the proxy can use that information and start the prefetch. We looked at the hit ratios in terms of where these different hits are coming from. Right? So I think this is just what you've seen before with the bar graphs. I think this is just a different version of showing it. So we also looked at the storage requirements here, right? So what you see is how much storage space do you need. And so what we did is actually here is to get these hit rates, right? We show that you need more storage. So that's the downside of it. You know, if you do basic caching, we can live again with what is this? With a terabyte here, right? Or a little bit more, actually. But then you would go up to 4 terabytes or something like this if you did the full 25 prefetching, right? So, but what we did is actually one thing different to the caching is what we did is since there's this uncertainty, right, about when you cache a prefix, you don't know if it's really what. When you prefetch, if it's really what, we only cache a prefix. So we only cache a certain length of that video, right? So we don't cache it completely. That's how you have this, you know, saving of, you know, too much wasting. But then you create your, you know, your additional buffer with that, right? So if you, you know, somewhere, did I have, so 30%, right? Now you get a 30% buffer on your local cache. And now while you start that, you can retrieve the rest of your video and hopefully make the experience as smooth as possible. Right? So that's what we're doing. So this was kind of simulations run where we assume we have an infinite storage space and just see when we hit the maximum here. And then we did the same simulation and we did the simulation over and over again with different storage sizes and looked it out here. Right? It's just to show how it changes when you have not the maximum 4 terabytes. 4 terabytes of really would go as small as storage. Right? So so I want to go to something I think is a little bit more interesting than just the storage size, and this is the question of, do we actually need to prefetch the whole video, or this is just a portion enough? And we went back to our local traces we did, right? And we looked at the average start buffer size that we would have needed to have a smooth playout. Remember we did this analysis and showed how many pauses we had? Based on that, we could say if we had buffered so much data, right, we would have had enough in our buffer to play out this video smoothly, right, with all the networking effects. And so you can see actually here, in all these cases we had, we averaged it out over the 10 videos we looked at, that 10%, 30, a little bit over 30. So in one case, and that was my terrible connection at the hotel there, over 40%. But usually, if you buffer 30, if you prefetch 30% of a video, you're always doing very well in these cases. Right? And so with that, we said, okay, if you request a video, you cache the whole video, right? Because it's coming into that subnet anyway. There's no extra load. For the prefetching, you only take 30% of the clip, of the initial 30%. Go ahead.
Is the percentage the right measure? Because some of the video clips are going to be very short, so it
Right.
will catch the whole thing.
That's a good question. Especially for short ones, it might be make more sense just to, forget about the percentage and get the whole video. Right? We hadn't looked at it, but that might be interesting to look at. You're absolutely right. So we did a little bit of a simplified analysis. Said, okay, here is a supposed the prefix size is 15% of the whole video, right? With N11 and caching whole videos and caching whole videos in addition. We look at what happens if you have nothing, if you don't do neither prefetching nor caching, right? And this is our normalized load. If we have cache only, we know that we have a 40% hit ratio. The load goes actually down by 40%, obviously, right? Because some of the requests don't even leave the subnet. If you do prefetch only, you have a cache rate of 66%, but you have an overhead of 40%, right? Because you load all these prefetch videos that are never watched, right? You prefetch all these videos that are actually never watched. And then if you do cache and prefetch and combine it, you have a hit rate of 74%, but only have an overhead of 2%. Right? So that's why we think this is a very efficient way of improving the user behavior there. Right? So we can actually improve that quite a bit by just including 2% of additional traffic. So this is, one way how we showed that, there's actually ways to improve your caching performance by information that's out there. We believe that recommendation systems are working very well. So I just want to, I didn't have time to go through the third topic I want to talk about, and I just want to show you something very quickly where you can even improve that further. So what we did is, we used the same traces as we had before, right? These traces I showed you. And what we did is now is, can we actually go and be the man in the middle and change what we recommend to the final viewer based on what's in the cache, right? Because what your recommended list would go through the cache. And I can now on the cache not change what content is on the list, but change the order of what's on the list. Why do we think that makes sense? Well, first of all, we see here, what you see here between these two traces, and they have been analyzed. There's two papers that are already out there, and then our current one, and they use two different traces in this paper. They use two other different traces in this paper, and then we had one trace for this work here, where you see that out of these traces we see that almost 30% or even higher are always coming from the related list in these traces. So it's used quite significantly by them, right? So with that we said, well, if this is used so significantly, why don't we use that to improve our caching rate again? So the idea is we reorder the related list based on what's on the cache rate. So you have a related, well, let me just show you. Let me jump ahead. No, before I jump ahead, one more thing I want to do. We analyzed this trace also a little bit further and looked at, through the API we can get the related list, and we can see where the users, what rank the users are selecting a follow-on video from, right? And here's the CDF of these two traces, and you can actually see, we have marked it here, that for 80% of the requests from the related list, it's from the top 10, right? So the higher the video shows up in the related list, the more likely it is that this one is selected. So our purpose was actually, we did some analysis. I don't want to go into detail here. I just want to show you the system. Is that if you have a related list that comes from the origin server or from somewhere high up like this, and you have these videos, you have B, C, and D already in the cache, right? You swap what you sent down to the viewer, right? So B, C, and D come on top, and A and E come on the bottom. And what we did then is we ran this also through with a simulation, and so the cache numbers are relatively low here, right? This is again the hit rate here, right? But if you see, and don't just look at the position centric here for this analysis. If you do no reordering, you have a 6.7% hit cache rate. If you do reordering, you almost double it. Right? Same here. It's even more significant for this second trace, right? It's like 4 times higher. Right? And so that shows you actually that with this little trick here, because by analyzing the user behavior, you can even further improve the behavior. Right? Because I think it's a kind of a natural behavior. You kind of click more on top. It seems like users are very lazy. They don't care too much about exactly what the content is. They just want to click on that, on what's high up. Yeah, go ahead.
So do the results actually come from a real experiment where you reorder things, or are you just assuming that users are click according to the position?
Very good. Big caveat on that. This is our expectation, right? We don't have a real experiment. So what we like to do now, and as soon as my student has implemented this, I would like to invite you guys. We will reveal this to everyone. We are thinking of building a little proxy, right? That does nothing else than changing the related list and see what the user behavior is, right? So what you would have to do is redirect your browser for this experiment, or watch a couple of videos, and show how you go through this. Right? And so hopefully with that we would get some more detail on the user behavior. In this case, in the simulation, that's probably the biggest drawback on that is we cannot, since YouTube doesn't allow us to do that. It's hard for us to analyze that, right? What I'm not showing you here is actually we did a bunch more of background analysis. Can we see if YouTube is maybe doing something like this already? We couldn't find any indications. What we also were concerned about, when do you get back to a loop by doing this, right? So how often do you actually click on videos from the related list until you come back to the video that you have selected initially? That's happening all the time already, right? So we just did again different sets of measurements, even planned like to see. We called it how the loop count, right? If you're interested, I can show you quickly here. We did a loop count study. You see, we used the different regions in Planet Lab, and actually, this is just taking, positions for the 100 videos we requested, and using the same position over and over again. So we're just saying we're using a very dumb user. So if you use position 4 all the time, right? You, after 4 videos, after not applying our scheme, just what YouTube is using today, after 4 videos, you come back to the original video. Right? So there's not much variety actually. So that's maybe why it also what could be shown before helps us with increasing the hit rate. Okay, so I hope I could show you a little bit of the challenges we have today in video streaming systems, multimedia streaming systems. I should say it's not just video streaming, but there's games. There's now kind of these small or thin client approaches where you stream just the frames. What the challenges on the server side are, but also what the challenges in the whole distributed system side are, how you can actually observe systems and use that information to think about new ideas to improve the performance of these systems. I'd be happy to take any additional questions you guys have. Also, I sit 2 minutes walking distance from here in the Knowles Engineering building. If you ever have any questions, you're more than welcome to stop by and talk to me. Any questions? And have a nice day.